So we have now Silvia Nagy, who's going to tell us about from gauge theory to gravity on curved backgrounds.
Okay, so you can hear me okay? Yeah, so first, thanks so much to the organizers for inviting me to this really nice workshop. And I have been thinking about the various topics that were covered here. So from the various things that people have talked about, you will see that I will touch upon integrable systems, but I'm more of a user of those systems than a developer. I would also touch upon black holes a little bit, which I know it's a topic that was discussed in previous weeks. What I will not have in my talk and what I don't know very much about yet is the machine learning aspect of the conference, but I would very much like to learn about it. So if anyone can spot anything related to what I'll talk about, even tangentially, that could be connected, please do come to me afterwards or tomorrow. I'm very open and very curious to learn about this topic. Good. So the work I'll talk about today was done in collaboration with Arthur Lipstein. This is a paper from earlier this year. And then the second half of the talk, the last bit, will be with Qiu Liang. This is a paper that we hope to put out sometime next week. Good. So broadly speaking, the kind of context of my work is the so-called double copy. And those of you who are here on Monday, I think you saw Mariana give a talk on this. And very, very simply, this is an idea coming originally from amplitudes that gravity is some kind of product of two Yang-Mills theories. And I'll be more precise on that word in the next few slides. And the goal of the talk, just in one line, is how can we take these constructions and extend them to curved background, particularly ADS backgrounds, and in particular away from scattering amplitudes. But to give you a brief overview of what the double copy is about, I do have to take a step back and give you a few slides on amplitudes to kind of show you the standard story, which bits of the standard story we want to keep and which we will discard. So the standard story starts from Yang-Mills gauge theory amplitudes, which let's take these are two different amplitudes for two Yang-Mills theories. They can be written in this very particular way. I hope it's not too difficult to read. I try to color this bit. So it's just the sum of things that look like Feynman diagrams. So you see these are the propagators here. And in the numerators, we have these products of what we call kinematic factors and what we call color factors. And these are nothing mysterious. So the kinematic factors are just the polarization vectors and momenta that you would expect in your scattering amplitudes. The color factors are just products of the structure constants of the non-abelian gauge group that we have in Yang-Mills. So in order to do this double copy, in order to go to gravity, we have to do two steps in a very simplified manner. So first, we want to arrange I messed up the colors here. We want to arrange the kinematic factors such that they behave the same way as the color factors. So what do I mean by this? Is that when I send one of these color factors to minus itself for a particular scattering amplitude, now it might not be obvious what this means. So I have a drawing here. So look at the top line here. So imagine here at the vertex, you'll have a structure constant. So if I flip two of the legs, I flip two of the indices on the structure constant, I get a minus sign. So that's all I mean here by sending Ci to minus Ci. Well, we have to arrange these amplitudes such that the NIs behave the same way. The second slightly more complicated relation involves a triple of these diagrams, and it just comes from the Jacobi identity for the structure constants from the non-abelian gauge group. And again, we have to organize our amplitudes such that the ends that don't a priori know about any gauge algebra behave in the same way. And you can immediately, like, those of you who are more mathematically inclined, you might immediately wonder, is this the sign of an additional algebra in Yang-Mills theory that we haven't yet properly discovered? And the answer will be yes, and I will show you a little bit more about that. So this was the picture. And then finally, once you've done these rearrangements, you are ready to quickly do the double copy. So there's actually two routes you can go. So from these Yang-Mills things, if you take one of the color factors and discard it, and replace it with the other kinematic factor from the other Young-Mills amplitude, then you get gravity. But then you might wonder, oh, I've lost all this information in these C's. So these were like all these structure constants. Well, it turns out there's another theory you can go to, which is the bi-adjoint scalar theory that we call the zeroth copy. So we haven't really lost any of the information. We've just repackaged it. Okay, so all of this was just sort of the setup, but we will be interested in going beyond the amplitudes program. So like I said before, because we found that there are certain symmetries and there are certain behaviors for these kinematic factors that look very, very much like those satisfied by structure constants, we expect this additional algebra in Young-Mills that we'll call the kinematic algebra. Now, as I mentioned, much of the intuition that we have for the double copy, it comes from the amplitudes. And amplitudes are mostly well understood when we do a perturbation theory around the flat background. So once we try to go to curved backgrounds for the double copy, there are a few proposals, but I would say that the status where we are compared to where we are with the flat space double copy, we are very, very far behind. And the reason for this is that much of our intuition and much of what we expect comes from amplitudes. So what we wanted to do, because looking at the full gravity theory in an ABS background is very, very difficult, we decided to work in a simplified regime, and this is the self-dual sector. And if you haven't encountered this before, it's a very, very useful subsector of both gravity and Young-Mills because things simplify a lot. So let me give you two definitions of it. The first definition, if you're more from a particle background, recall that your gauge field and your graviton have two helicities, +1 or -1. So when I do scattering amplitudes for either of them, I imagine, a mixing of all these helicities. Now, the self-dual sector simply means that I throw away, say, all the negative ones and keep just the positive helicity. So I would be looking at processes that are just in terms of, say, positive helicities. Now, you can see that this actually throws away a lot of the information in my theory. So I'm really restricted to a small subsector here. And this will be a very good toy model. As we'll see, it is integrable and a lot of things, just work very nicely here. But I wanted to make the argument that it's more than just a toy model. So the reason why we like it is that it's not just kind of a special case where we test our theories. It's also the starting point of a different perturbation theory that you can do in these theories. So just to kind of recall for those of us who do physics, we usually think of the standard perturbation theory, where at the bottom here, I have the weak limit. So this is what we call the linearized theory. Nothing interacts with anything else. So this, imagine just going to quadratic order in your Lagrangian, say for gravity, then we can keep adding more and more terms that you can roughly think of as having stronger and stronger interactions. And these ticks here I put are like how well we understand the very general double copy. And my opinion is that as soon as we go a little bit away from here, we have, good understanding for amplitudes, but for general fields, not so much. But anyway, my point was about the self-dual sector, which is a completely different way of doing perturbation theory. So here at the bottom, I have the self-dual sector. So I have, like I said, no particles with minus helicity, and all of them have plus helicity. However, we do have a controlled way of then looking at processes where I take one of these guys to be negative, then I can put one more to be negative, and so on, going back to the general theory. So in this sense, you could think of it as a starting point rather than just a sort of fake idealized model. Good. You can stop me at any point, by the way, if you have any questions. Okay, but for those of you who are more geometrically inclined, more field theory, we have this second definition of self-duality. So for Young-Mills, I just take the field strength, I just apply the Hodge dual on it, and then equate it back to itself. So this is kind of self-explanatory in the name. So dual equal to itself, i.e. self-dual. And then for gravity, we play a very, very similar game where we start with the Riemann tensor here. We dualize over two of the indices, and again, we equate to the original one. And one can see that these two definitions are indeed equivalent and the same. Good. So, okay, now that we went to this sector, there's a further simplification that we can do here. And this is working in the right kind of coordinates and going to the right kind of gauge. And this was found many years ago. So it turns out that if you go to the light cone coordinates, which hopefully are familiar to people, if not, they're just very simply related to the Cartesian ones, and then going to light cone gauge, which just means I set this first guy here to 0, it turns out for Young-Mills, the entire field can be written just in terms of a scalar. And intuitively, this should make sense from the particle picture that I showed you, is that now I only have one helicity, so only 1 degree of freedom roughly, so I should only have one scalar describing my theory. And I put a bold phi here, so I'm not writing the gauge indices, but you should imagine here that we have non-abelian gauge theory. So this scalar is valued in the Lie gauge group. Good. Similarly, you can do the same for the graviton, and as we'll see in a moment, here we introduced a little bit of notation. So you can take your space-time and split it into two-dimensional subplanes, and then this is your metric. And then we introduce these constant tensors, which are anti-symmetric. Basically, you can think of them as the epsilon tensors over these two planes. So anyway, after introducing this bit of notation, it turns out that your self-dual Young-Mills and self-dual gravity fields can just be written in terms of this really simple form here, in terms of these scalars. And the point that I want to emphasize here is that this is really non-perturbative in the standard sense of perturbation theory. So I'm allowing here any sort of interactions with the restriction that I just have one type of helicity. So I haven't thrown away anything from the Einstein equation, except I've imposed this constraint. So even though this H looks like a fluctuation, this H is basically the full G when I add eta. So yeah, this I've emphasized here. So this is just how you write your fields in terms of the scalars. Then the dynamics of all of this, it turns out, is incorporated in these very simple looking equations. So on the left, we have the Young-Mills. So again, these are, you should think of as matrices, these phi's. And on the right-hand side, we have the gravity, which is just a standard scalar. Now, at this stage, it turns out that it's useful to introduce this Poisson bracket, which, as you recall, this pi is just an epsilon over a subplane. And now we can write these equations of motion in a very, very suggestive way. So you see for Young-Mills, I have the propagator and then the interaction, which turns out which is just cubic, is like a combination of the commutator from the gauge group and this Poisson bracket. And then for gravity, I have this double Poisson bracket, which I think is basically just this. So if you stare at this for a bit, and then you stare at the definition of the Poisson bracket here, you see why we like to write it in this way. So basically this operator that defines my Poisson bracket, I'm acting with it twice on these phi's. So this is kind of just a notation that we've introduced to make things more suggestive, but if you're not happy with it, you can just read it from here. Good, so then the double copy prescription, which was done a few years ago now by Ricardo Ricardo Montero, Donald O'Connell, was to just do this replacement. So just send this phi of Young-Mills to the phi of gravity and simply send the commutator to the Poisson bracket. So remember from the amplitude story, we threw away the color factors. So we threw away the structure constants and we put back in some kinematic factors, which corresponded to momenta and polarization vectors. Now, the momenta you should think of as these derivatives that sit in the Poisson bracket here. So what we do is we throw away the color factor here and we put another kinematic factor. And I think I even have a diagram here which now mimics what was happening in the amplitude story. So we start with the Young-Mills guys. You can do a replacement in this direction to get your gravity, or you can do a replacement in the other direction to get your biojoint. Good. Now, the thing I want to emphasize is that here now we're not just doing amplitudes. This is the equation of motion fully governing the self-dual sector in this gauge. So this is kind of everything physical about the theory is contained in these equations. In particular, you could look at exact solutions, etc., and some people have. But what I wanted to show you quickly is just some older work, because this relates a little bit to the integrability of this sector. And then there's an interesting question later on when we go to ADS backgrounds. And this is the kind of symmetries that you expect to have in this setup. So recall that we took our Young-Mills and our gravity, we wrote it in terms of these simple scalars. Now, the question that we wanted to ask was how much of the original symmetry of the Young-Mills or of gravity preserves this rewriting. So we're looking for residual symmetries preserving this form of the self-dual. So this is your Young-Mills symmetry. So here, remember what was happening, that two of the other components of the gauge field were vanishing. So the AI, for AI to vanish, we just want the gauge parameter here to not depend on the I coordinates. Recall how we split our coordinates here. So if we make the lambda only depend on the Y, then you can see that I can preserve this. And I can even read off the transformation of the scalar directly. So don't worry about the details of this. The point is that I can really do away with the vectors that I started with and do everything I want just in terms of these scalars. Now, for gravity, we kind of play the same game again. So recall this was a non-perturbative rewriting. So we take a general diffeomorphism here and we ask, how can I preserve this? And after a few lines of calculation, you find this, what we call the first family. So this is just a diffeomorphism parameter. We see that it has to be restricted in this particular way. So again, two of the components are 0. This guy depends just on Y. And again, we can read off some phi. So up to here, we've just found some residual symmetries. Good. Now we put them together. We kind of stared at them for a bit. We wondered if the symmetries themselves double copy. So here the idea was, how much freedom do I have in this double copy procedure? Is it just specifically for the way I've written it in terms of the scalars, or is there a little bit of wiggle room where if I do some gauge symmetry here, I get some diffeo on the other side? And at first staring at this, it looked a little bit hopeless until we realized that we can repackage the gravity transformation in this really nice way in terms of the Poisson bracket that we had earlier when we were writing the equations of motion. So this Poisson bracket, which governs the algebra, turns out to basically appear everywhere where you want to do your double copy. And then the Young-Mills residual gauge transformation looks like this, the gravity looks like this, and you can immediately see that you get the double copy without changing any of the rules you had before, and you just have one additional rule where the gauge parameter lambda goes to this lambda of gravity that was built from the diffeo parameter. So remember, this B was just this component of the diffeo parameter. Good, so this was nice. This was some non-perturbative subset of symmetries, which had not been observed before, by the way, because until before, only linearized symmetries had been kind of noticed to double copy. But I wanted to show you a little bit to kind of make contact with the integrability side of things. Okay, here it's just a little bit of notation. So again, here was just if you want to go back to the Young-Mills and gravity fields, you can again see the double copy nicely, but we can leave that for now. Now, we wanted phi, this variation of phi, to preserve the equations of motion for self-dual gravity in terms of the scalar. And then we found that we have to restrict this a little bit further, and we introduced this operator notation S for redefining our lambda. Anyway, this is all a bit of notation, so don't worry about the details. Again, this is just to say that we have this rewriting now for Young-Mills and gravity, and now I can write my double copy rules in this kind of new way. And this seems a bit unnecessary relative to the previous slide, but you'll kind of see the point in a moment, because as I kept saying, this is an integrable subsector. And this means that we have an infinite tower of charges. And in particular, those correspond to an infinite tower of symmetries. And this is something this is not something we noticed. This is something that was known before, but the symmetries had not been worked out explicitly. So what was known in the integrability literature about these systems is that if you start with your self-dual equations that I wrote previously, and I assume that I have some symmetry of these equations, so some delta phi that is a symmetry, i.e. I have this equality, which, as you remember from the previous slides, we already found some. Then it turns out you can, for free, get a new symmetry that we call delta tilde via this recursion relation. So once I have some little bit of local symmetry in there, I can apply this recursive process and I can just get myself an infinite tower of symmetries. And these, of course, will give you an infinite tower of charges, and these are related to vanishings of the amplitudes in the self-dual sector, etc. So there's an infinite tower of symmetries here. And we kind of worked out, of course, we didn't work them out explicitly, but we wanted to see how they're related via the double copy and what they correspond to physically. And this is what we found. So this top line here is what I've shown you already. So this was some subset of gauge symmetries, went to some subset of diffeos. Then at the next level, we found some other subset of diffeos, but at this stage, what we had on the Young-Mills side was no longer a gauge symmetry. And this is because these are additional symmetries that only the self-dual sector possesses, and they don't exist in the full Young-Mills because otherwise the full Young-Mills itself would be integrable. So we have this big tower, and then we have this nice set of double copy relations that you can write, and this is why this extra notation was needed here, because at nth order you have some subtleties about the factor, but that's just a detail. The point is they're always related in this way. So the integrability in one part is directly mapped to the integrability in the other one. I had to mention here there's some alternative work where people have constructed lax pairs for these theories. And again, there you can see also the double copy at the level of the lax pairs directly, which it should be an equivalent statement to what we have here. Good, so this was all flat space until now. Any questions on that? Yes. Yes. Yes, it's defined as an operator, as a differential operator. I don't remember it explicitly, but it's kind of written in terms of this Poisson bracket. A differential operator where it acts kind of like this Poisson bracket, but only with one of the derivatives. And then you kind of see the double copy because roughly one of them has something like the commutator and one has something like part of the Poisson bracket. It's not as kind of clean as here, but you can kind of see that it's built from these kind of ingredients. Good. Yeah. Sorry, say the last sentence again. Yeah, so in amplitudes, it's also a replacement. Good, if you're talking, so there's two kind of types of double copy that you have in amplitudes. And one is the older story that's called KLT, and this came kind of from the string story, where it's a real product. Maybe you remember it, and then some kernel and stuff. And that works up to some point where it starts getting difficult. But then the reason why the field kind of got revolutionized and a lot of people started working on it, I should have said this in more detail. There's this other version called the BCJ double copy, where the amplitudes themselves work by replacement rather than product. And it turns out, and it's kind of, I do take your point, because at a conceptual level, it's somehow less satisfying that I don't have, a mathematically properly defined product. And I will say something a bit about that in the second half of my talk, if I manage to get to it. But kind of the advantage this has, it's just, it works amazingly well. So we've sacrificed some mathematical kind of elegance for something that just turns out to work really, really well. People have been studying a lot and trying to find an explicit thing, but like an explicit product, like you say, and it works in certain special cases, and I'll mention in a bit. Good. So now we get on to the, yes. So yeah, when I say curved space, I mean in the simplest possible first step that you can do. So we add a cosmological constant and we focus on de Sitter or anti-de Sitter. Even with this, everything looks more difficult in general. We no longer have amplitudes. As I said, we have correlators, which are generally quite difficult to compute. But what we set out to try to do earlier late last year with Arthur is kind of seeing how well everything worked in the self-dual sector in the flat case and how nicely it showed us the double copy rules. We just wondered, can I do a self-dual version of gravity, but in an ADS background? So not in a flat background, because we thought, even forgetting about the double copy, we thought this could be a very nice toy model where I could maybe compute correlators. I could ask about integrability. There's also these W infinity algebras that appear in celestial holography. Do we see them here? So we kind of, a lot of questions that are just difficult to do in general ADS or DS. We wanted to find a toy model where it's easier to set this up. So just to go back a second, first to self-dual Young-Mills, what it turns out that here you don't get anything new. So I'm going to work in Euclidean ADS, and this is my background metric. The self-duality condition just looks like this, where now I have the root G. Now, it turns out, because this metric is conformally flat, if I plug in the factors of G carefully here, and I remember this was raised with G, and I look at the left and right-hand side, it turns out that self-dual Young-Mills on a conformally flat background reduces to just the same equation as flat Young-Mills. And this was known in the literature already. This isn't something that we found. So in the Young-Mills side, you don't really get anything new. And again, because we knew that the light cone gauge was important, here again, we went to the light cone coordinates, and this was our metric. Good, so let me just I feel really bad about this, but this is a slightly different notation from what I had before. So recall we had this gauge field, and it was written, only two of them were non-zero. We had this equation of motion, we had the splitting into the two planes. And what we found that we had to do is that we just wrote these operators slightly differently. So now my Poisson bracket is written as an epsilon, and then these pi's, which are differential operators, given in this way. So it's basically what we had before, just repackaged slightly differently in a way that will be easier to generalize later to ADS. But then again, the equation is just what I've shown you already. Okay, so this was Young-Mills. Now let's go to gravity, and let's ask, what would it mean to set up a self-duality equation for gravity? So recall this was for the flat one. We just dualize over two of the indices of the Riemann tensor. And one of the sort of physics kind of consequences of this is that you're equating. So you see, if I take this equation and I contract two of the indices, I'm equating the equation of motion in a flat background to the Bianchi identity. And this is exactly what we expect, because if you think about dualization, what it does is that it mixes Bianchi identities and equations of motion. So self-duality, it's the special point where they're exactly equal. Good, so this was in a flat space. Now we wanted to extend this to curved space. So what we did is we introduced this tensor that we call T, which is just a deformation of the Riemann tensor that depends on lambda, my cosmological constant, and then some G's chosen such that the indices work out the right way. And then we simply define the self-duality relation in terms of this T. When I contract two of the indices here, it turns out that it gives me exactly what I need. So this is this you should recognize as the Einstein equation with a cosmological constant. And on the right-hand side, again, I get the Bianchi identities. Yeah. Very good. So I think the next slide should answer your question, maybe. Is this what you were getting at? Yeah. Yeah, so it's basically the way you should think of the T. Okay, so let me just go through this quickly. So remember the Weyl tensor in GR. This is something you would have learned in a first course on GR, that when I apply the equations of motion, the Weyl tensor becomes equal to the Riemann tensor. Now, the tensor that we used, it turns out that when I take the Weyl tensor and apply the equations of motion, it goes back to my T. So you should think of our T as the Weyl tensor, but on the support of the equations of motion. So I have these lambdas explicitly here. Good. So that I think that is kind of what you're asking. And this makes sense for those of you who are kind of used to the spinorial representation of GR, because you remember the helicities are encoded in the decomposition of the Weyl tensor. So this is just an aside. Good. So now, finally, let's see. So now we don't have such an obvious notion of, we don't have scattering amplitudes or helicities in the same obvious way, but it turns out we can still have a very nice scalar description. So again, with the notation that we've introduced here, I can write this was what we had in flat space. Sorry, this is just a reminder of the flat space one, because I want to compare. Okay, so let's go to ADS. So let's kind of do them. I wish I could have put them on the same kind of slide. Okay, so this is what the metric looks like in self-dual ADS. Everything is again just governed by a scalar phi. I'm again in a gauge where almost everything vanishes except 3 of my components. So these alpha betas run over this. And now you see, whereas in flat space, H was just these 2 operators acting on phi, with these operators given here. Now my H is this kind of mixture of pi and pi tilde, where pi tilde is a slight deformation of the pi's that I had in flat space. And this is given exactly by the conformal factor, well, the square root of the conformal factor. So it's a very, very slight deformation. So it wasn't too ugly. It wasn't too bad or too far away from what we had in flat space. And then finally, the dynamics of self-dual ADS is governed by this simple equation. So here we have the kind of propagator part. We have this m squared, which is -1. That's a conformally coupled scalar. And the interaction part is again very similar to the flat one. So you see, just like how for the metric itself, we had a mixture here of these 2 operators. For the interaction term, instead of this double Poisson bracket, we have this mixed Poisson bracket. So the interior one is the old one of flat space. The exterior one is this modified Poisson bracket that I'll say some more about on the next slide. So the modified Poisson bracket is given in terms of this new pi. So now I've written it all here again for your convenience. It's given in terms of a mixture of the old projectors from flat space and the slightly modified ones. And what's kind of nice about it, and what we found interesting, is that it still satisfies the Jacobi identity. So this bracket still corresponds to some Lie algebra, which is some additional symmetry that you find in your gravity theory. Just like how in flat space you had this double Poisson, now we have this double mixed Poisson. So there is definitely additional symmetry there that we were not aware of before. And moreover, it forms an algebra. So we have the we have a Lie algebra satisfying the Jacobi identity. And these are just some formulae for this bracket. Good. Any questions so far? Okay, so we've also looked, maybe I shouldn't go too much into detail here because this is more of an amplitudes related kind of thing, but now you can compute correlators, and this sort of new algebra that we've defined, you can really think of it. So this bracket gives you something like a structure constant, except it's not a constant now, it depends on momenta. And this, our modified one, has now a modified structure constant here. And we've constructed this sort of 3-point vertices for self-dual Yang-Mills and self-dual gravity. And again, at the level of correlators, you can see how by replacing the color part here, you get the kinematic part. And actually, at the moment we are, so this was for the first paper, we kind of did just a 3-point example, but at the moment we are looking at higher order correlators in these theories. And it turns out that these sort of relations, these nice relations continue to hold when you compute these higher order correlators in these theories. And in fact, relative to flat space, where if you're just trying to do scattering amplitudes with the same helicity, most things vanish, what we find that in ADS, these correlators don't actually vanish. So actually they contain more information than in flat space. Good, and then finally, this is, I guess, for people who sort of follow the celestial holography program, there's a sort of big symmetry algebra found there called the W1 plus infinity algebra. And it turns out, so this is something that's really, again, related to being in the self-dual sector. And it turns out that you can work it out from this Poisson bracket. I don't want to go into much detail, but what we found is that there is actually a modified version of this W infinity for our modified Poisson bracket as well. So maybe I will, yeah, and this is some current stuff that we're trying to do here. And then maybe before I move on to the second half of my talk, any questions on that? Good. So, okay, something that I do want to mention before I move on is this question, because we feel that this model should be integrable, but we haven't proven it yet. So what we've tried so far is, like I was showing you, this recursion relation for symmetries in the flat case, which gives you an infinite tower. This is kind of what we started looking at. Perhaps one could try to construct lax pairs as well. Maybe that's something we wanted to try, but we haven't yet. So that we think is an interesting question, because then we also want to see any relations to ADS CFT. Good. So now for the second half, I want to go back to this question I got earlier about having a more precise double copy where it's like a very well-defined product. And this is something that I used to work on some years ago, and then I sort of abandoned it for a bit, and I kind of came back to it. So going back to our two perturbation schemes, we've kind of talked about the right-hand side so far. Well, we've looked at the simplest case on the right-hand side, but now let us go back to kind of the more standard perturbation theory. And in particular, I will just look at the weak limit, where I'm doing linearized theory. And here I will try to connect a little bit with black holes. So because the linearized theory is so simple, here we can be a bit more ambitious, and we can try to construct arbitrary gravity fluctuations. So in principle, without trying to fix a gauge, without trying to restrict to any sector or specific solutions, from arbitrary Young-Mills fluctuations. And what we found that in this context some years ago already, it's useful to work with the BRST formulation. So just the usual QFT BRST formulation with a slight modification that I'll show you. And this has a lot of benefits. And it kind of gives you some very precise map that I'll show you. And again, you can think of it as a starting point of some perturbation for going to higher orders. And this perturbation has been done in certain versions already. It doesn't work as nicely as the kind of weak limit, but you can use this definitely as a building block and go to higher orders. But what I want to kind of look at today is not the higher orders, but instead going from flat space to curved space again. Okay, so as a kind of, let's see, some of the things here in the interest of time we can ignore. So we're working in the BRST formulation. So we have this is your standard Lagrangian, like Young-Mills or gravity Lagrangian linearized. I put some gauge fixing term here. Recall I end up with some ghosts. My usual ghost. What we do that's slightly different is we used to couple some sources to these ghosts, and they contribute to the double copy. And then we required, we want to write a dictionary for these. Let's just focus on the important bits. So for the graviton fluctuation, in terms of the linearized Young-Mills fluctuation, such that I can get all the linearized solutions. And it's also robust, fully robust under symmetry transformations. So what we require is that if I do become a BRST symmetry. So recall now what happens in the BRST setup. It's instead of the gauge symmetry, I just replace it with a ghost. When I do a transformation on this form, I just get a diffuse transformation. So a change on the Young-Mills side that's unphysical should correspond to a change on the gravity side that's also unphysical. That's sort of the point of this robustness. So again, this was some time ago, we found that this is the kind of product that you should write. So again, when we do the double copy, even at the simplest level, we don't just get the graviton, we also get some antisymmetric thing and a dilaton. But for the purpose of the talk today, we can ignore the antisymmetric bit. And what we find is that you should construct your graviton fluctuation in terms of this circle product. So what this circle product we found should be is this double convolution, which is defined just in the usual way between Young-Mills gauge fields and this inverse bi-adjoint scalar. And if you remember from the amplitude slides, when I was taking the 0th copy and I was getting something with just color and 2 copies of the color indices, that this is exactly the scalar from that theory. So this one kind of captures all the degrees of freedom in some sense of if I do a double copy. Good. So the crucial points, remember our requirement was that when I do a transformation like this, I'll end up with a linearized diffeomorphism. Now, the reason why this works is because we have this convolution and it satisfies this non-Leibniz rule. So I can move my derivatives around as I wish. So you can kind of picture here, if I hit this with a symmetry transformation, the derivative that comes from the gauge symmetry kind of, the derivative that comes from the gauge symmetry here can go outside via this rule and give me some of these nice things where I can just read off my ghost. So anyways, this was an old story from some years ago, but what I want to emphasize here that will be important for generalizing to curved space is that this convolution is not just a random product that, well, we found useful because it has these properties. It also has a physical meaning, and this is that if you go to momentum space, it becomes a product, as you might know already. And in terms of amplitudes, one should think in the dual space. So one should think in the momentum space. And when we do the double copy in momentum space, we really want to take both Young-Mills guys to have the same momentum. So it's kind of natural to use this type of product, and it also has the nice mathematical properties that we need. Okay, and then kind of to make contact with an example for a physical solution that you can obtain from this. This is called the J&W solution, and it consists, it's sort of a naked singularity. It consists of a graviton fluctuation and of a dilaton fluctuation. Like you can write the full non-perturbative thing. This is just a linearized part, where these m and y are arbitrary parameters. So this is like an infinite family of solutions. And in particular, if you set your y to 0, i.e. throw away the dilaton, then you just recover the Schwarzschild solution. So somehow the simplest solution that you kind of want to get to test your double copy. And for this simple solution, it turns out that if you're kind of interested more in the physics, what you should remember is that on the Young-Mills side, what we put in is a point source. So I just have a point charge, non-supersymmetric, it just has electric charge. This is how we write it. This is the Young-Mills field. I have to also put in some ghosts. Remember, I'm in the BRST form. This is my spectator field. So after all of that, it turns out that I can write my graviton in terms of these Young-Mills via the map. So the Schwarzschild solution comes from the point source in electromagnetism. And then what happened with the ghosts is that they were controlling the dilaton. So if you look at the dilaton kind of dictionary, it's made up not just of products of Young-Mills, but also products of these ghosts. So in particular, if I want to set the dilaton to 0 to just get Schwarzschild, I can do this by an appropriate choice of these ghosts. So anyway, this was all the story in flat space. Now let me quickly, because I think I'm running out of time, let me now go to the curves. And any questions on the flat space? Maybe I was a bit quick there. But let me be very brief and show you the main results and the main issue we had and how we found a sort of partial solution, I would say, in ADS backgrounds. So remember, the main goal was to, well, one of the goals was to get the symmetries of gravity from the symmetries of Young-Mills. This is kind of like a robustness check. And once you go to a background that's not flat, you immediately run into the issue that, see, here I now have nablas rather than partials. Like now I will see the Christoffel symbols of my background. And okay, one thing you might ask, which turns out to be very difficult to solve because we spent quite a lot of time on it, is can you modify the definition of your convolution itself in some clever way such that this kind of thing still works? And it turns out for some very special cases, such as two spheres and three-dimensional Einstein static universes, we did manage to do that. However, for something like ADS, we didn't. So we kind of did the next best thing. So we'll have to restrict ourselves a bit. So we'll be working in the sitter. So this is some work with Kuya Liang that we're just finishing. So working in the sitter, we found firstly that it's convenient to work with the conformal metric. So this is again similar to the metric that I was using in ADS before. This is the conformal one. And now I notice that my covariant derivative, so I and j here are just run over the axis and 0 is the eta direction. Now I notice that this is what my covariant derivative looks like. And we kind of thought, okay, we don't know how to do the full thing in general, but let me go to temporal gauge and only look at residual symmetries that preserve temporal gauge. Because you see, if I allow myself to kill all vector components that have a 0 index, my sort of nabla collapses back to a partial. So I've kind of solved this first problem here, because on the gravity side, again, I'll just have Hij, and one can check that the thing kind of goes through just like in the flat space. But I want to emphasize that this is only true for the symmetries. When we'll go and look at specific solutions, then we do keep information about the curved space nature, because when I write my Einstein equation or even the Maxwell equations, there will be some other nablas that do contribute. So there one has to be careful. But for the symmetries, this seemed like a good setup. Then the second kind of component, so we're almost there. The second component was this thing I said that in flat space, what the convolution corresponded to was a product in momentum space that can be seen via the Fourier transform. So that was just the convolution theorem. Now that was because flat space has translation invariance and the Fourier transform is the natural thing to do. If you're in the sitter space, the natural thing to do turns out to be the Mellin transformation, which captures your scaling symmetry, because we no longer have the translation symmetry, but we have this rescaling symmetry, and this is just what the Mellin transform looks like. So that finally, to kind of get the full dictionary, the convolution that one should use is this mixed convolution where over the spatial components, I do the spatial one, and then over the temporal component, I do the Mellin. I do something like a Mellin convolution. And the way I wrote these things kind of emphasized the symmetries of the space. So you see for the spatial bit, I'm integrating over all possible translations. So you see I have plus x and minus x. And then over the temporal thing, I'm integrating over rescaling. So I have tau and then division by tau. So this kind of makes the symmetries of the space manifest. And again, as I was saying, when I go to the dual space, it just becomes a product. So here K is the momentum and S is this parameter from the Mellin transformation. And then finally, we write this again the same way. And then just to kind of, this is the dictionary that we found. So we didn't look at the two forms. So this is for H, as I said, we're in temporal gauge. This is the dilaton. The details of the dictionary are not important. What I want to mention is that I have some free parameters here, these A's and B's. This is because at linear level, we always have a little bit of freedom. So the dictionary is not fully fixed, but we'll see that a very simple version of this will correspond to the solution we're interested in. And just as an aside, one can easily go to ADS, where instead of going to temporal gauge where I set A0 to 0, now I go to another axial gauge where I set A3 to 0. So it's very, very similar, and one can write a very similar dictionary. But let me just show you, because I think this is a very nice result for an explicit black hole solution. So we wanted to go back to a situation where in the flat space, we know exactly what we have. And we wanted to ask, does this generalize immediately and nicely to the sitter? And here recall that the kind of knowledge from various ways of doing the double copy, really not just from the convolution, is that if I start with a point source, I should end up on Schwarzschild. And this is a point source solution, but that we had to massage and put into temporal gauge. So if you see this weird eta dependence, so it looks like it's time dependent now, this is just because this is what happens when you do your gauge transformation to put it in temporal gauge. But this is just a standard point source solution in ADS. Now, this you should hopefully recognize is just a standard Schwarzschild black hole solution with a cosmological constant. So this is in the standard coordinates. What we had to do is to go to our coordinates, then linearize, then go to temporal gauge. So it was quite a lot of work because we couldn't find this in the literature. But by the end, the result, so at first when we looked at the result, it looked very ugly to us. So this is the linearized Schwarzschild solution in temporal gauge. And it looked very ugly to us. So we thought, oh, this is why it's not in the literature. But after we stared at it some more, we realized that it actually has this very simple form. Now, I don't know if anyone has seen it anywhere before, do let me know so we can cite it, but we haven't found it anywhere before, where it's just this double derivative of 1 over r times some factor that depends on eta. And notice that the Yang-Mills linearized point source has a very, very similar expression. So that we thought, oh, that looks very nice. Then we took this and plugged it into the dictionary, and we found that it works with a very, very simple. So it turns out that we could set this A2 to 0 and really work with the simplest, really simplest kind of double copy dictionary you can think of, where I just multiply these two guys via this convolution product. So we had to do all the Mellin and Fourier transforms of these guys, multiply them in the dual space. So in practice, this is how you do the calculation, then Fourier transform back, and then you find that you reproduce this guy from these guys. And there's also some ghosts, and we also set the dilaton to 0, so everything kind of is consistent, but I just wanted to show you this kind of main result, which we thought was quite nice and simple. And maybe because it's almost 5, I will just end with this kind of pictorial big picture thing, which is how we're trying to attack this double copy from the simpler. So remember, we had the self-dual symbol case, we had the weak symbol case, and then what we try to do is go away from these simple models, however way we know best. So I'll just leave you with this, and I should finish. Thanks.
So thanks for the talk. So are there any questions or comments? Yes.
You seem to have introduced two double copy, well, at least two double copy prescriptions.
Yes.
One is the Kershal prescription, which you involve somewhere there in the middle, and then this latter one. How are they related?
Do you mean the replacement one from the self-dual versus?
I meant the double copy prescription for relating gravitational backgrounds to Yang-Mills backgrounds.
Oh, I'm not relating the background. Sorry, I should have been more, sorry, maybe I wasn't clear about that. What I'm doing in this version of the double copy is I'm not generating the background itself. So I start with the Yang-Mills that already sits in an ADS background, and I'm only looking at the sort of the fluctuation.
Fine, but you had that also in the double copy in the Kershal relation, right? You write the metric as a flat piece plus a punctuation.
Yeah, in the Kershal, it's actually a bit different, because for Kershal, you can kind of do a different version of it where I think you can generate your ADS background from some Yang-Mills background, which is in some ways nicer than assuming that you start on an ADS background. The problem with that is that we really don't know how to generalize beyond spaces that are of that form. So in this case, yeah, in general, what we seem to be able to handle better for more general situations is where we start already with the Young Mills on the background.
Any other comment or question?
Is there like a universal dictionary for a language, or always that you have different systems, you find different dictionaries?
Good. So that's kind of what a lot of what I'm trying to do. And this is kind of the picture. Yeah, the answer, the short answer is a universal one that works nicely, no. But what I'm trying to do, so yeah, maybe I should explain this picture a bit more, is that we want to look at kind of subsets of the theory that are not fixed solutions or specific quantities, where you have some way of going away from it towards the full theory. So I would say in these simplified setups, we can do it. There's also some very nice results for specific solutions, which would say around here. So I would say there's still much to kind of fill. What we were hoping with this second half of with this convolution stuff is kind of what we were hoping to achieve, because that's really general. So I'm not assuming any solutions, but that kind of sits at the weak thing here. So when I try to go to stronger, we haven't managed to formulate that in this really nice general way. So then one has to invoke knowledge from amplitudes and one has to do replacement rules again. So yeah, that's just a long-winded way of saying that it's still very patchy in places. Yeah.
Thank you very much.
Can you show again your slide with the convolution for ADS?
Yeah, so this guy, yes, this guy.
Yeah. So do you know it, or do you expect it could hold beyond the linearized order in some different precision? I'm just wondering, because you have a product in momentum space, and for amplitudes, like, well, correlators in the CEDAR or ADS, the double copy fails once you go beyond 3 points in momentum space.
Yeah, I mean, there's kind of a lot good. So firstly, I mean, beyond linear, I don't even know in flat space how to do it. If you mean the convolution itself, that we don't even know in flat space, right?
Nice.
But to kind of go, I think maybe you're asking, can I use the knowledge from, in flat space, I would use then the knowledge from amplitudes to do some replacement rules. So this kind of now goes back to here. If I wanted to go to higher orders, I would want to use something from correlators. And like you said, there's not an agreement like how the double copy works for correlators in general. And this kind of motivated the work in the first half of the talk, which is what we did with Arthur, which let's look at this simple setup where we have more control. So now we're actually computing some higher order things that seem to have a much nicer structure than what was tried before in the general theory, except of course we're in this restricted self-dual theory.
That's still in momentum space?
That's in, that we do in momentum space. And what you can do then is not go to the full thing, but say I have my weak ADS here via the convolution. I would maybe go up, use the self-dual thing to kind of go a little bit into the,
Thank you.
for those specific correlator, yeah.
Okay, any other question? If not, let's thank Silvia again.